Okay, Calc. I've written up some kind of whiteboard problems. I don't know if you want to write these down on a whiteboard or if you want to do them on a piece of paper so you can look back at them however you want to do. If you need to pause the video to go grab a whiteboard, you just do whatever. And then as you go through these problems, I don't know if you're watching as a class or you're watching individually, but if you want to pause also and try to solve them for yourself and then, like resume as we go through each one of them, that would be a good strategy. But I will go through each of these. There's like maybe 11 questions, maybe. And some of them are fast, but some of them do take a little bit of time. Like number 1 takes a little bit of time. I have my assistant here. She's eating a rice cake. So if you hear her squawking, yeah, you'll hear her squawking. She's just being my assistant today. So, okay. All right. In all of section 5.1, we did like looking at area under curve. So you have a curve and then you're doing like the left end points and matching them up and trying to add the towers together and all that good stuff. Okay, so that's what this first example is looking at. And I don't have a very good calculator, so bear with me. I might abort mission on some of these calculations and just have you guys finish them. But this guy is the function that we have. Hey. And this is the square root of, I like to write it as the square root of x plus 1, okay, instead of 1 plus x. And what that's going to do, what this plus 1 does, you don't have to know this, but it's just helpful to know. That moves him 1 unit to the left, and a square root function looks like that little thing that jets out. So he's like 1 unit to the left, and he looks something like that. And they want us to find the area under the curve from 0 to 1, okay? I'm gonna zoom in on him a little bit. Let's say 0 is here. I'm going to make this really different units and such. Let's do this. I'm going to say negative 1 is there, and that way I can say positive 1 is like over here, right? So negative 1, positive 1. We want to find the area from 0 to 1. So I want to find like this chunk right here, okay? So in order to be able to do that, I'm going to put 4 rectangles in there, and I'm going to start with the left end points, okay? So I'm going to start with the left end point, left end point, left end point. These are all like touching there, and then left end point. So each tower is just slightly taller than the other one, okay? Now this is going to be an underestimate because this is not filled in, right? Like there's little chunks and stuff. So that's going to be underestimating, and then all we need to do is find out what the base of each one is, what the height of each one is, and then add them all together, okay? So to do this, I know that the base of each one is, if we're going from 0 to 1 and there's 4 of them, the base of each one is going to be a quarter, right? So 0.25, 0.25, 0.25, 0.25, okay? Rather than taking base times height plus base times height plus base times height, you guys know this, we take the base and we shove it out in front and then we add all the heights together, right? Which is basically like just, it's an easier way of doing a calculation. And then all we have to do is find the heights of each one of these, okay? So here's the deal. To find out how tall this tower is, I look at like just this coordinate point, right? This coordinate point is the point 0 comma something, right? This coordinate point would be the point 0.25 comma something. This coordinate point would be 0.5 comma something. This would be 0.75 comma something, right? And to figure out what those somethings are, I plug it into the 1 plus x, that stuff, and I take the square root, and that will give me the height, right? So if I plug 0 in, 0 into there, I guess into the x, 1 plus 0 is 1, the square root of 1 is 1. So I know that the first tower has a height of 1. This guy has a height of 1, okay? Then the second tower, I got to think a little bit. If I add it in there, that would be 1.25, right? So I got to take the square root of 1.25, and I have my phone calculator, so bear with me. Hold on just a second. Okay, now it's not turning on its side. Oh, there we go. Okay, 1.25. And I get like 1.12. We'll just go 2 decimal places. So 1.12. If I plug in 0.5, that's 1.5 in the square root. So 1.22 is his height. 1.22 and 1.75 if I plug the 0.75 in. 1.75, the square root of that is 1.32. Hey, that was really kind of like coincidental. How nice. Okay, so when I add all 4 of those things together, I get like 66. But I still have to multiply by that by 0.25 on the outside. So 0.25, 4.66. And I get an area of 1.165-ish, according to how I rounded. That's the left endpoints, 1.165. And that's what his area is. Okay, now, using the right endpoints, I'm going to leave my work here, okay, for the left endpoints, because the right endpoints are just going to slightly change him just a little bit. Okay, now, my first tower is going to go off of this right side. Okay, my second tower is going to look like this, according to this right endpoint, right endpoint, right endpoint, okay? And this tower is going to go off of here, so slightly taller, okay? Now, the deal here is, this first tower now is as tall as the second tower was previously. So instead of this first tower being 1, he is 1.12, because that's the height of this dot right here, okay? This dot makes that second tower 1.22. This third tower is now 1.32. I've gotten rid of this 1, and now I've added on this fourth one over here, and that I get by plugging 1 in. Okay, so now I need this coordinate point 1 comma something, and if I plug 1 in, I'm going to take the square root of 2, which I should know that. It's like 1.47 or something like that. Give me just a second. Yeah, oh no, 1.41. Okay, 1.41 is what he is. Okay, so now I have those numbers instead for the right endpoints, okay? And I'm adding those guys together and then taking 0.25 of that. Okay, so if I add those together, I got 0.25 times, blah, blah, blah. Should I try to do that in my head? That's, I think we're asking for trouble if we do that. Plus 1.22, plus 1.32, plus 1.41. And I get 5.07. And I'm going to take that times 0.25. 1.2675. 1.2675. So, and again, the right endpoints is going to provide an upper estimate. So like an overestimate, because all of this area is, accounted for, that shouldn't be accounted for. So we know that our actual area is going to be somewhere in between those two, not necessarily in the middle. It's not necessarily the average of the two, okay? Now, if we wanted to narrow that window, you guys know the answer to this. Do more than 4 rectangles, right? Do 8 or 16 or 100, right? Heaven forbid we actually have to do that. But that is how that works. Now, why do this process if we have, like, a better way to do it, right? This process sometimes is the only method that you have when you have really, really super ugly things that you can't even do, like, substitution on. Right? Sometimes there are equations that are so ugly that you have no choice but to do this. And a lot of times a computer system will do it for you, right? Like they'll set up a computer system if they need to know areas, like this would be like a graphical representation, or like, you know how we talk about like volume, right? And displacement. We'll do that down below. If we're trying to find volume and displacement and distance that we've traveled and all that good stuff, and it's a really ugly formula, we will use a computer system to do that for us. Okay, but this is the process that it's doing. Okay, let's go to some faster ones. 2, 3, 4, 5, 6, 7, blah, 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 all this good stuff, okay? You're going to look at this, and this is an indefinite integral. We have no limits of integration, but it's like, do I just do the thing, or do I have to use substitution? Because those are my two options, right? This one's just x to the 2/5 power. I don't have like two different functions going on, so here I'm just going to take the antiderivative, okay? Like the straight thing, the 1 over n plus 1 x to the n plus 1. That's the formula that we are using. So in a sense, we're taking this 2/5 and we're adding 1 to it, which is going to make it 7/5. So I have 1 over 7/5 x to the 7/5, which in turn is going to, if we flip this to the top, 5 over 7 x to the 7/5 power. Don't forget your plus c, because this is an indefinite integral. So that is that. You don't necessarily need to put him back into... Whoa! Did you drop them all? My goodness sakes. You really sound sick right now. You know that? I think you were faking so you could snuggle. Silly girl. Okay, so that was number 2. Number 3, they don't have it ready to go for you in the form that we needed to be in. So this is x to the 1/3 power. That's what we want to do. And then we don't have to use substitution here. We can just do the whole 1 over n plus 1 x to the n plus 1. If we add 1 to that, that's going to be 4/3. Okay, so in front, I'm going to skip some steps now, is 3/4 x to the 4/3 power. And then don't forget your plus c. Okay, now, when you're taking this test, I would kind of just in your brain, like, think about, like, okay, if I take the derivative of this, do I get back to this, right? I would take the 4/3 down in front. 4/3 would cancel with the 3/4, so I have no number here. And then I subtract 1, which is going to make him to the 1/3 power. Yep, I did all that right. Okay, so just kind of like glance at it and see, like, taking the derivative, does that give me what I need? Okay, number 4, do we need to do substitution? I don't think so, but I don't like this 3. Anytime you have a constant, you can bump him out in front. So I'm going to just do the 3 here and just deal with the e to the x power. Now, this is going to be on that one sheet that you guys had. I don't know if I laminated it or not, but I think it's in a different color. And what's the antiderivative of e to the x? Well, the derivative of e to the x is e to the x, right? But what's the antiderivative of e to the x? That would be e to the x as well, right? So if I'm taking the antiderivative of this guy, he is just e to the x plus c, but I need to make sure I strap that 3 on there. So that was kind of an easier one, maybe, just because e to the x is his own derivative and antiderivative. Now, it gets complicated when you have like e to the 2x. That's not necessarily going to be e to the 2x, right? So that's where it gets a little hairy. But this one for now is okay, okay? How would you do e to the 2x if I was taking the antiderivative of e to the 2x? Okay, in this case, you would have to say u equals 2x, and then du would be 2 dx, and you'd have to divide by 1/2. So I'd have 1/2 e to the u, and that type of thing. Okay, if that confused you, it's fine. But, yeah, for those of you wondering, when I slapped that up there, that's how you would have to do that in that case. Okay? All right, number 5. Do I have to use substitution? Nope, you don't. This one, 1 over x squared, I'm going to make him x to the negative 2 power when I move him to the top. And then I can just do the 1 over n plus 1, x to the n plus 1, right? Okay? So if I add 1 to this exponent of negative 2, he will be to the negative 1 power. So x to the negative 1 power. That means, what the matter? You still have one? Right. Okay, that means my exponent out front, or my number out front, is 1 over negative 1. Okay, so this is negative 1 x to the negative 1 power, or negative 1 over x if I bump him back down to the bottom. Oh, don't forget plus c. Did we do plus c on all the others? Yeah, we did. I'm proud of us. We remembered our plus c's. Okay, so there's that. I'm going through these kind of fast, so, you know, if somebody's stuck and they're like, I don't know how we got that, somebody else please help explain, okay? Or star it and I'll go through it again tomorrow. Hold on, we got an assistant that's unhappy. Oh, come here. You're going to be my close assistant? Okay, what do you want? Hey, do you want this? You want that? Okay. All right, number 6. Do we have to use substitution? Actually, yes, we do in this case. You will know you have to use substitution when you have a function inside of another. They call it a composite function. I know you guys have heard that word before, where a function is composed inside of something else. So x plus 9 is stuck inside of the 5th power. So that's what I'm going to use as my u. And then du, the derivative of x is just 1. The derivative of 9 goes away, so 1 dx, or just dx in this case. So this case, I don't have anything to divide over. I'm just done, and I'm going to start to substitute. Okay, so my integral symbol, he goes down. This guy is now going to be replaced with u to the 5th power. And then dx, right here, dx becomes du. That's what he's equal to. Okay, and then now I do my antiderivative. So antiderivative of u to the 5th is 1/6 u to the 6th. Don't forget plus c. And then last thing I have to do is plug my x plus 9 back in. Since I don't have limits of integration, that thing, I don't have limits of integration to plug in. So I just make him look nice. And there you go. Okay. Next. Number 7. Ooh, this one I put in here because it's kind of tricky. Like, he looks like there's like 2 parts going on, but like, what do I set as my U? So we kind of have to play around for a little bit. Okay, here's the trick. Pause it if you want to try to figure this out on your own. Okay, if you haven't already. Okay, but here's the trick. U is ln of x. Do you remember what the derivative of ln of x is? It is 1 over x dx. Okay, so here's the deal. This guy, if you want to rewrite him, it's helpful to do this. Okay, I have my integral symbol. I'm going to slide this ln of x off the top. So I have ln of x times, that would be 1 over x dx. Oh, look. If ln of x is my u, this is now u, 1 over x dx, this guy right here is du. Okay, so I really, when I do my substitution, I've got my integral symbol, and then I've just got u du, right? And that's it, okay? So think about it in terms of like writing this differently like this, and then that can maybe help you. But yeah, ln of x, it's been a hot second since we've done ln's, but the derivative of ln of x is 1 over x. Hey, we playing the pickup game? All right, how do you do the derivative of u? Or the antiderivative of u. This is u to the first power. So it's going to be 1/2 u squared plus c. And then all I need to do is add in this guy right here, what u was, okay? So he is 1/2 ln x squared plus c. I think somebody asked me once, like, can you do that like ln squared x? Sometimes they will write it like that, like they do for like sine. Instead of writing it as sine x squared, they'll write it as sine squared x. Yeah, I think I have seen this before, not as often, but you can certainly do it. The one thing that you want to avoid is writing this, is avoiding this as ln, or avoiding writing this as ln of x squared like this. You want to take ln of the value and then square it. And when you write it like this, it makes it look like you're squaring the x first and then taking ln. Okay, so you want to avoid doing that. But this is what your antiderivative should look like. And that is that. Okay? All right, 8. Now we have a definite integral where we're plugging stuff in. Do you have to use substitution? I see parentheses, so it looks like I'm going to have to use substitution, except I don't have an exponent here. So this is literally just x minus 1, and I can take the antiderivative of that and just plug in my numbers. Okay? So why are those parentheses even there? And it has to do with the fact that like dx is being applied to the whole thing. Otherwise, it would look like 1 dx, like it's just those two that are joined together instead of this whole thing. So that's why there's parentheses, is that the dx applies to all of it. Don't do that. Don't do that. Okay? So the antiderivative of x is 1/2 x squared. The antiderivative of -1 is minus 1x. And I'm going to use my notation so I know that I plug in 0 and I plug in 1. Okay? And I'm plugging 1 in first, right? The top number goes in first. Not the bigger number, right? But the top number. Okay? Minus what I get when I plug in 0. And you guys should know this already. If you don't want to write this all out, you don't have to, because the 0 is going to go away. So he's gone. And now I just have to do this. So 1 squared is 1 times 1/2 is 1/2 minus 1. Honey, goodness. What? Oh, goodness. Oh, goodness. Yes. Okay, so -1/2 is that value. Okay, now how do we get a negative? X minus 1 is a linear function down at -1. He goes like this. So if we're finding the value from 0 to 1, he is underneath of the x-axis. So that's how he is. Okay, do you need a toy? Yeah. Well, I can't help you with that. You want to go down? No, we don't want to go down there. We're going to start fussing. Okay. Now we're on 9. Find the area under the curve of blah, blah, blah. Like, what the heck? How do I do this? This is just the same thing as what you were doing in number 8, that they just wrote it differently. They just wrote it out in words instead of... Do you want to go in the other room and play? What do you want? Do you want to go over there? Okay, so they're just writing in a different form. So area under the curve, we've got from 2 to 3, x squared minus 2 dx. And this is the same as what number 8 was then. So 1/3 x cubed minus 2x, plugging in 2 and 3. 3 first, then 2. Oh, I'm running out of room. I didn't give myself enough room. So if I plug 3 in, 1/3 3 cubed minus 2 times 3. That's plugging 3 in. 1/3 2 cubed minus 2 times 2. I think I plugged that in right. 3 cubed is 27. 1/3 of 27 is 9. So 9 minus 6 is that guy. Minus 2 cubed is 8. Ugh, this is going to be like 8/3 minus 4, which is 12/3, which is negative 4/3, but we have this minus here, so this is plus 4/3. Plus 4/3. That was kind of a mess, and I hope I did that right. This is 3 plus 4/3, and this is 1 1/3, so that's 4 1/3. That was kind of a mess. Area under the curve, 4 1/3-ish, something like that. Okay, that was done really fast. So if you need to pause and go back, you just do whatever you need to do. Okay, next one, number 10. Find the displacement of a particle between 0 and 2 pi of cosine of x. Okay, when they ask for displacement, I'm just going to think about what cosine of x looks like. Boop, boop, boop. Cosine does one of these between 0 and 2 pi. Here's 0, here's 2 pi. Okay? All right, displacement means like where am I at in relationship to where I started? Or in other words, like it's just like finding the integral, right? Like where is my area at? Am I more positive area? Am I more negative area? I didn't draw this very good, but some of you guys might know the answer to this. I'm going to say that my area is going to be 0, right? Like my displacement is 0. So I've gone, this is me going to the right direction. Okay, my velocity is going down, so I'm slowing down, but I'm still going to the right direction. So this is me traveling to the right, and then under here, this is when I start to travel to the left. So I'm backtracking for a little while, right, until I get to here, and then this is me traveling back to the right again. And I'm going to end up in the same spot as I was to begin with, okay, because my areas end up matching up, okay. So let's see how this works. Displacement, and that's another way of saying exactly the same thing as 9 and 8 we're saying. Okay, find the displacement. So I'm going between 0 and 2 pi, and cosine of t, the dt is what my ending thing would be. Okay, so displacement, I'm finding where I'm going to end up. The antiderivative of cosine is sine. I don't think it's negative either, because the derivative of sine is cosine. Yeah, so we're just going sine of t from 0 to 2 pi. Okay. All right, well, sine of t, I guess, hold on, back up. We got to plug in 2 pi. Sine of 2 pi minus sine of 0. All right. 2 pi, if you need to look at your unit circle, 0 is here, 2 pi. Sine is the y-coordinate. So over here at 0, we're at 1, 0. The sine value is this one. So this is 0 minus, I guess sine of 0 is in the same spot as 2 pi. This is 0, and 2 pi is in the same spot. So that would also be 0, so 0 minus 0 is 0. Okay, just like we said over here. Our displacement is going to be 0 because I've done some work. I've gone some distance, right? But that would be total distance and not displacement. Okay, so how do we figure out displacement, or like how do we figure out distance, right? Well, knowing what the graph of this looks like, what I would do is, if we want to find total distance, is I would find the distance from here to here and then take it times 4, right? Because that would be, it's like in 4 chunks, right? I want positive distance. So if I look at the distance from here to here, now what is this mark right here? That is pi over 2, right? Because here would be pi, if that's 2 pi, right? So I would find the distance from pi over 2 and multiply by 4 is what I would do if you were trying to find total distance, right? But displacement is where we're going to end up relative to where we started. So there's that. All right, 11, last one. Find the displacement of a particle between 0 and 1 if my velocity is t to the 5th power. Okay, I'm not going to draw this one out, but we know that displacement just means where I'm at relative to where I began, right? Okay, and so that is just evaluating the integral from 0 to 1 of t to the 5th power dt. Okay, so very easy. Just do this like normal. 1/6 t to the 6th, plug in 0, 1. So basically I'm just plugging in 1 because I know that 0 is going to end up canceling, like this goes to 0, right? So 1 to the 6th power is 1 times 1/6. I am just 1/6 of a unit further to the right than I was previously. Okay, there you go. That is how that works. All right, that was a decent review. We'll maybe do a little bit more tomorrow, and then we'll test on Thursday. Okay? All right.